Hi everybody. Okay, so today I'm going to go ahead and record this video, in fact the video you're watching right now, to be able to go over assignment 5 in a little bit more detail as basically a stand-in for the labs that can't happen this week because of the global pandemic that you might have heard of. Okay, so I already went through the majority of this document, assignment 5, genetic algorithm for procedural level design. So I'm not going to do that again. The long and short of it, though, is what we need to do is we need to implement a GA, genetic algorithm, that is able to fit a number of given evaluators and some held out ones as well. So I'm going to just go ahead and assume you've watched the other video so that I don't need to reintroduce a whole bunch of these concepts. But suffice to say, if we play it, notably, we're going to get just this random garbage over and over and over again. Okay, so let's go ahead and open up Level Optimizer. This is the basic script that you will be modifying for this assignment. And specifically, you will be modifying this getLevel function. Now, notably, you can make changes elsewhere in this Level Optimizer.cs script. Anywhere you want, you can make a change in this particular script, but this is the only script that you should be turning in outside of if you use some stuff from prior assignments. Then you might turn some stuff in there as well. There's more information on that right at the end of this document as per the usual. But by default, all you're turning in is this level optimizer.cs file, so it's the only place you should be making changes. So let's take a look at this. So what we're doing right now, if we take a look at this default code, is we're going to instantiate our random population. We are going to set up a best candidate so far and a best fitness so far, set that equal to 0. And then we're basically just going to iterate through our population, which again was just this random setup that we originally made of some set population size. And we are going to find the best fitness, and then we're going to return the candidate with the best fitness. So a very straightforward thing. So what we could do instead here, right, is we could take a look at the pseudocode that you were all given for genetic algorithms. So I'm going to go way over to here. Nope. Yeah, geez, this is a long lecture. Okay, so here's our pseudocode, right? So the first thing to note is that this first line is already done for you, right? Population equals initialized population size, random points. So we've already created a population of population size composed of random points. Next, we need to set some time variable equal to 0 if we're going to use that to keep track of things. So I'm going to go ahead and right here, make this change. Now, notably, you don't have to make this change like this. In fact, you know what? Let's go ahead and remove this and just handle it this way. So I'm going to go ahead and insert our while loop right here. So we're going to have our main while loop right here. So that means that we should probably go ahead and set up our time variable for making sure that we haven't gone for too long up here. So then the very easy thing to do is to do while time is less than max attempts rather. By default, that's this constant variable up here. Again, you don't have to use this, but it could be helpful. Let's go ahead and increment time in here. Okay, so that's this nice basic thing. You'll also note that we have a secondary check that I give you right here. If the average or the best fitness in this population is greater than some threshold, we should also stop. So let's go ahead and add that as well. So and best fitness, oops, I forgot I'm not in Python for a second, and best fitness so far, if I can learn to spell one day, it's greater than, say, let's see, what's the grading cutoff for this assignment? I believe I set it to, where are you? 0.9. Okay, so we can go ahead and just use 0.9 because once we've hit at least 0.9, we know that we have the best possible fitness. So if either of these two things have happened, if either we've gone through up to our max attempts or we've already found something with the best possible fitness, we can go ahead and stop. But until then, let's see what else we need here. First of all, we should mutate the population. So as a reminder, the way that mutate the population works is that with some probability, aka a mutation rate, we want to randomly swap out a member of our population with a random neighbor. It has all the benefits of a random walk. So let's go ahead and just, in our code over here, write mutate population. So then what we need to do is we need to iterate through our population, right? So we already thankfully have code that we can do that with. That's right up here. I'm not going to actually add more things to this. But in here, what we can do is we can use our mutate function, right? Now, notably, we don't want to always be mutating. We want to mutate according to some mutation rate. So what we can do is we can say if population I, or no, we just want to do it randomly, right? So if random.value, random.value is just going to give you a random value between 0 and 1, is less than the mutation rate, which will occur, in this case, 20% of the time, right? So a fifth of the time this will occur, roughly, right, probabilistically. Then what we should do is we should mutate this particular level, okay? So all we need to do here is go ahead and call our mutate function. So we can do population I is equal to, now note, population is composed of levels. So we're going to go ahead and pass into mutate population I. Okay, cool. So there's the mutate population portion done. We iterate through our population. Well, in this case, we're iterating through a number through our population. The reason why we're not just doing like a for each loop and going through our population that way is because we're going to be changing our array as we go. So we don't want to be going about it that way. Instead, we're going to do it this way, just a little cleaner. Then, roughly 20% of the time, we're going to mutate this particular level. Now, notably, you can change this mutation function. You might actually even find it helpful for some of the evaluators. But right now, I'm not going to. All I'm going to do is leave this as is. Okay, so this is going to be the mutate portion. Let's go ahead and go down here to the next bit, which is the crossover population portion. So right here, crossover population. Now, I'm not going to write this for you, or rather, I'm not going to just give you code that you can just use for this section yourself, because honestly, it is very similar to this code. In fact, you should be able to just copy and paste and really only make a change in terms of the function you're calling and how you're adding instead of replacing something in the population. So this should be extremely easy. But just as a reminder of what a crossover should do, inspired by reproduction, what we should do is we should sample pairs from our population based on their fitness and mix their traits. So in other words, we need to find how good various members of our population are, what the fitness of various members of our population are, and then we should sample according to their fitness. Now, hold on a second. That sure sounds like this function, which is already given to you. Probabilistically samples a level from a population based on its fitness. So really, all we could do, if we knew how many times we wanted to iterate through our crossover, let's just say I'm going to do it once for now. Make a child equals to crossover sample population sample population. Now this won't work because sample needs a little bit more than that. Let's take a look here. Sample takes in a population, an evaluator, and a goal value. Okay, that's fair. So then we want to pass in our evaluator and our goal value. And here again, evaluator and our goal value. Okay, so I've just produced one child. Oh, I should state the type. It's a level. So this is our one child level. I'm just going to go ahead and add it to our population. Now, this isn't quite enough to actually do our crossover. For one, we shouldn't just be producing one child every generation. We should be producing some number of crossovers of children every generation. That's variable. It's up to you. And also, handled like this, we're not guaranteed that I've given you two different levels. I might have actually just given you the same two levels with the sampling approach. So you're going to have to do a little bit more work than that to get that working. Okay, so then we need to reduce our population. So the way that we want to handle that is, right, so after crossover comes reducing the population. All we need to do there is reduce our population back down to the initial size, taking only the best population size members. Okay, well, let's see if there's happens to be a function for doing exactly that. Oh my goodness, why there is. It takes in a population, the population size we want to use, an evaluator, and the goal value. It's going to return the best members of this population of population size, so the best population size members of the population based on this evaluator and this goal value. So let's go ahead and run that. So now we're going to do population equals reduce population, population size, evaluator, goal value. So there's one problem right here right now, which is, notably, that we're not actually checking through to see what the best candidate so far is and what the best fitness so far is. So let's go ahead and change that. For each level L in our population, float this fitness equals fitness L evaluator goal value. Give us the fitness of this level. If this fitness is better than best fitness so far, go ahead and say, oops, best candidate so far is equal L. We might actually go ahead and clone this just to make sure that we don't have an issue with referencing later on. And then best fitness so far equals this fitness. Okay, super duper simple. We got our mutation, we got not quite a right crossover, and we've got a reduce. Let's go ahead and run back here, see how things work. So I'm going to go ahead and hit the button again. Now at most, oh, we got a null reference exception, so that's not good. Let's see how I broke this. Looks like line 78 is the culprit. Oh no, line 19 is the culprit, way up here. Game handler, line 19. We don't have the start position for our levels. Whoops. How did that happen? Set in case this level changed when the ghost spawned. What the heck? Did I make changes and then forget? That's very possible. Oh, is it that this hasn't been instantiated yet? Let's take a look. Go to declaration. No, that should all just be set up. Oh, I see. Go start pause is never set. Okay, well, pretty easy change here. If you're running into this issue, this wasn't an issue the last time I ran the code, but I might have made some changes without thinking about it. If level go start pause is equal to null, is non-null, first of all, then we can do this. And otherwise, feel free to go ahead and make these changes. I'll use these changes when I'm running your code. Agent constants.go start position just shouldn't change. Okay. Oh, no. What's happening is we're returning a null level. Whoops. No, don't make these changes. I'm just a fool. All right. I forgot to make the one last important change to our level optimizer. Oh, we're never hitting a best candidate. Is that it? That's interesting. How on earth are you returning null? Let's see here. So our fitness we're getting is 0, so we're never iterating through it. Oh, did I do this while loop? I did. I do the while loop the wrong way around. This should be less than. Okay, easy. We just never iterated. Okay, so there we go. So I made all those nice changes. I made the changes to the mutation rate. I made the changes to the crossover and the reduce. And still, our fitness was only 0.22. That's not very good. Let's try this again. Again, 0.197. That's not great. 0.264. Also not great. Let's just check here what the evaluator is. So the evaluator is claustrophobic evaluators. This is the one that wants to be entirely enclosed. If instead, or rather entirely not enclosed, we can instead replace this with obstacle lover, and it should be really easy to get a high fitness. Yeah, 0.837. Still not perfect, but pretty darn close. Hungry evaluator. Let's see this. 0.6542. Okay, so a few things here, right? Obviously, I didn't actually implement crossover correctly. We talked about that. That's why this isn't working. So there's that potential issue here. There's that potential problem. But there's some other things that we could tweak here as well. So notably, we could tweak this mutation rate. So if we're more random, if we're making more random changes more frequently, then that will lead to more variance, which will lead to exploring more. The other thing we can do is we can up our max attempts. Right now this is only 100. That's not very long. We could go all the way up to 1,000, right? We could say, all right, we're going to try 1,000 times to find a good level. Let's run this again. Okay, right? Those two changes alone, and we already are hitting 0.902857 for our hungry evaluator. Now, what happened there, right? What happened there was all we did was we made this more like a random walk, and we let our code run for longer. That's it. Now, just making these changes is not going to be sufficient. Let's go ahead and head back here. Let's go ahead and do our claustrophobic. Okay, 0.904, very good. 0.904, very good. Okay, well, let's see here. If you just make enough random moves long enough, you can eventually get it. Nice, 0.9, great. Try that again. 0.9, wonderful. Okay, well, you know, it does seem like we're having no problem getting any of these. Very cool, very cool. So essentially this is the power of a random walk, right? Via just doing a random walk for long enough, you're able to find good enough levels according to these various heuristics. Now, I will warn you again that these heuristics, these three evaluators you're given, are relatively straightforward. There are more complicated evaluators you are not given, and so just making these changes is not going to be sufficient. But if you fully complete out your code, in other words, if you finish out this crossover population thing, you'll be able to hit them no problem without making any other changes to this code. So it's a relatively straightforward thing, right? It's a very, very simple thing to do. The basic point of this assignment. That's by design. It is by design that this basic setup should be pretty easy. You should be able to get these 10 points relatively straightforward. What I'm really honestly interested in is seeing people try for these 2 extra credit points. So this one, making things playable, that's way harder, right? The basic idea here is that we should be able to come up with a path between wherever Pac-Man is and wherever the pellets are. That's tough, right? Now, maybe we could do something with the Pathfinder. So let's take a look here. How we were doing pathfinding in this assignment. We take a look back at FSM agent, the way you're handling your set target. All right, homework 5, navigation handler, instance, node handler, closest node. So notably, you're not going to be able directly to call Homework 5 Navigator Handler because you're not going to be able to call the what's going on with your Homework Navigator Handler. You're not going to be able to call it because it hasn't been set up yet. But what you could do is you could get your own version of a Pathfinder, or just copy and paste some code in there, right? If you have a Pathfinder, in this case, there's a Greedy Pathfinder that you're given. Greedy Pathfinder. Boop, boop, boop. You can make a version of this that would allow you to figure out, inside Level Optimizer, is it possible to go from the Pac-Man starting location to anywhere else that you'd want to go, right? To be able to collect all the pellets. That's a lot more computation, and as a reminder, there is a time limit on this assignment. As it is right now, it's set up as 5 minutes running on my laptop with your code, running in headless mode, which is not an insignificant amount of time, but if you're finding that on your laptop or on your computer, wherever you're doing this assignment, that you are having to wait for many minutes, maybe you need to look at making your code a little bit more efficient. But anyway, this is one way, one idea, one hint of how you could handle that extra credit of trying to make playable levels. The other thing here is to make distinct styles, right? We talked about ways of doing that, and in fact, I gave examples of particular kinds of changes that you could make in the original Assignment 5 intro video, so I'm not going to do that again. But as a reminder, you'd want to be making those kinds of changes on a per level basis with code in Level Optimizer, because that's the only code that you're going to be turning in. Don't make just changes in level or something like that. Okay? All right. So with that, I have given you a skeleton here for a code that with very minor tweaks will be able to get a 10 out of 10. It's going to give you like, I don't know, 6 out of 10, right? No problem. The only issue is these remaining 4 points. So you can already get a passing grade with just turning in this assignment. If people actually watch this video, if you just turn in this code, you'll get a passing grade. Well, no, that's not true, is it? No, yeah, because you'll get 3 of the evaluators, but 3 of the withheld. So you'll get 3 points. Okay, so you'll get 30%. I'm still being very nice here, I think. This will give you 3 points just by default. Finish it out. Finish this crossover thing. Maybe write your own evaluators to check to make sure that you should be able to handle these other ones. That'll give you the remainder 4 points when you finish this crossover thing, and it'll give you the remaining 3 points once you've ensured that you can handle any evaluator, right? Then, from there, it's a relatively straightforward thing to start thinking at least about these other 2 extra credit points and what you could do for them. I'm personally really looking forward to seeing what kind of levels y'all come up with. I'm sure that you're going to come up with things that I would never think of, so I'm looking forward to that. I think that's it for now. As a reminder, you can always reach out to me via email. If you have particular questions on the assignment, please feel free to post on Piazza about that. I think that would be helpful to anybody trying to actually do this final assignment. Okay? All right. I will leave this right here so that you can see this code as the video ends. You can just pause the screen if you want, so you can see that baseline, so you can copy it over. And otherwise, talk to you on Friday.